Okay, good afternoon and welcome. This is the second term webinar series for Further Maths, focusing on the Recurrence and Financial Mathematics module. My name is David Tynan, and if you want to read that, you can. And today we're focusing on recurrence models for linear growth and decay. So we'll look at the basic idea of recurrence and direct rules as an alternative, and then look how those models could be used for applications to simple interest problems, depreciation, both flat rate and unit cost. So we'll start with just the basic idea. So I'll move across to the calculator here, and we'll just talk about a sequence generally. So let's say you wanted a sequence starting with 20, and then you want it to increase by 3. So if you have to list successive terms, if you just press plus, the calculator will assume that you mean to do something to the previous answer. So answer plus 3, and press enter, and then if you press enter again, it will repeat the step of adding 3, and this process is called recursion, where the next answer is based on the previous answer after some operation, in this case adding 3. I'll do it one more time. And then obviously this is not bad for working out a couple of terms, but if you have to generate a number of terms, you might think, well, there must be a quicker way, and it's pretty obvious just looking at this that a way to get to the number 32 would be to say start with 20 and then do 4 lots of 3. And so that introduces the basic idea of a more direct rule. Okay, now because there is a particular notation used in Further Maths, as students you have to get used to that. It's used across the module. And so I'll just click to the next page, 1.2, and you'll see there's a template here. This template is a notes file. For those that haven't used notes or the notes application on the calculator, it's designed to allow you to combine text information and to do mathematical calculations. And in this case, we'll be using it quite a bit today to have a look at linear growth and decay based on recurrence models. So if you've started the module already, you'll be up to speed with this. But if you're not, the first thing to think about is there a way to describe the relationship that we just looked at, starting at 20, jumping by 3? And the notation in the recurrence relation is that you can calculate the next term, so the value of the n plus 1 term, the term next, and that's equal to the current term plus some d, or difference is sometimes a good way to think about it. So the rule is, in general, v of n plus 1 is v of n plus d given some v0, which is where v0 is the starting value. So in our story, or the one that we just simulated, the v0 is 20 and the d value is 3. And so our particular recurrence rule is this one here. V of n plus 1 is v of n plus 3. It describes the recurrence, that the successive terms are calculated by getting the previous term and adding 3, with the special condition that you start at 20. So if you've done this in year 11 Further Maths, you'd be familiar with it, but it's just a revision of the general idea. So the notation that's used here hopefully is not too difficult, but some students do find the n plus 1 and n business a little bit confusing. So it just takes a while to get used to. Now, as I said, it's good if there's a direct rule. For example, what if you wanted to know what the 17th term here would be? What happens if you want to know when does the thing reach a value of 200 or 1,000? You don't want to be pressing enter and then counting how many times that you can do it. So this direct rule is pretty much what we did on the previous screen. That is, the nth value, or v of n, is equal to the starting value, v of naught, plus n times the number of differences. So, in a case that we just used before, our rule would be, or direct rule would be, v of n is 20 plus n times 3, where 3 is our difference. So if, for example, we did 4 as the n value, that is 4 jumps up from 20, then v of 4 would be 20 plus 4 times 3, or 32. The next thing that's happening here is that the first 5 terms are generated. So the first 5 terms in this sequence you can see listed there. So the notes page is a really convenient way of doing a quick analysis of a basic recurrence relationship, in this case a linear one where it's just something being added each time. And the final thing there is to say, okay, well, is there a way of calculating the n value if you know that the value, or the v of n, was 100, what would the n value, how many times would you have had to have added the 3? And the calculation there is shown. Now, I probably should show you a little bit under the hood for those that haven't used notes pages before. So I'll just start at the top. Just for convenience, there's I've shaded in yellow the bits that the user or the student would enter. So in this case, we've got a variable called v0, and if I click in it, I can change the value, say, to 10, and that will be reflected throughout. I'll put it back to 20. Oops. Try again. There we go. Okay, so that's essentially how it's working. And these little boxes here are maths boxes, so they're live. So any change to those values might affect values in any other calculation formulas that we've used. So I won't go through those in great detail, except to say the one down the bottom. The one down the bottom is saying, okay, well, how do you find the n? And that's clearly a solving technique. So if you look here, it should be no surprise that there is a solve command that is working out what the n value would be based on the value of 100 and the direct rule. So I hope that sort of goes some way to sort of introduce the idea of a recurrence relation and the associated direct rule. And it occurred to me I did forget something back at this screen, so I'm going to go back and do it now. And I saw this little trick that's quite good as a way of simulating and keeping count. So I'll just do that quickly. So let's say that you started and your V0, that is your starting term, is 20. And then you wanted to add 1, and then your common difference of 3. And now if you press enter, not only do you get successive terms in this sequence, it also gives you an index number to tell you which term it is. Okay, so that's the basic idea. Now I'll just go back to the PowerPoint thing, and we've just covered the basic idea of linear recurrence rules and their associated direct rules. And now we'll look at some applications of that where we can use the recurrence rules to model. I'll now switch back to the calculator and I'll go to 2.1. Okay. So 2.1 again is a notes page, and you can see that there's the familiar recurrence relation at the top, shaded in grey. It's generally the same, it's the same rule that you use for simple interest. However, it has a slight complication, and the complication is that for the D value, the difference between successive terms, you need to work out what that value would be. And if you think about it, let's say that you invested in some system $320, which is listed there, and the rate is 7% simple interest. You could work out what the value of the interest that will be added each year would be by just saying what is 7% of 320. So the formula on the right there for D is that calculation, 7 over 100 times 320. So that generates $22.40, I guess, interest. And so in writing the particular recurrence rule that goes with this particular simple interest story, the rule would be V of n plus 1 is equal to V of n plus 22.4, where the original value, or the V0, is $320. Similarly, you may be quite interested in when does your money, when does it get to $1,000, or what happens after 5 years, or something like that. So in that case, you need the direct rule, and if you've done the work above in the recurrence rule, it's not too difficult to see how you would jump to a rule that says that the V of n is V of 0 plus n times D, in this case particularly 320 plus n times $22.40. Note, a feature of simple interest is that the amount of interest each year is constant, so you will always be adding $22.40 for every year that you have such an investment. Okay, when the n value is 5, you'll notice that it can automatically change. So you're able, because that's a yellow shaded box, you can just type in a new value. Let's say n was 20. You could put in 20 and it would recalculate it. I'll just scroll down a little bit because it doesn't quite all fit on the same screen. And like the previous page, which for the general idea of recurrence, this little line will show the value of that investment based on simple interest over 5 years. Now, those of you looking very carefully will notice that there are 6 entries in that list. And the reason for that is, if you think about V0 being 320, and over a 5-year period, so after 1 year it's 342.40, after 2 years 364.80, and so on. So there are 6 terms there, but the first one is denoted V0. So V5 is still 432, representing how much the value of that simple interest would be, of that investment would be at the end of 5 years. And finally, there's a calculation there, similar to the one on the previous page, for saying, for answering those test SAC exam questions that say, how many years would it take for that investment to grow to $1,000? And I'll just click on it so you can see. And it should be no surprise, it's the same formula basically as the previous page. Okay, so that's the idea of using a notes page just for simple interest. The other thing I want you to notice is that this doesn't, you might think, why doesn't it say 1.3 here? And the reason is because we're using variables like V0 and D and N, and we want them to be only specific to the simple interest application. If you remember back on the previous page, we had defined V0 and D and N, and we don't want those values to mess up these values. And so when you insert a new problem rather than a new page, it keeps those definitions of the values, any variables and any functions, it keeps them separate. Okay, so I think that's probably enough on simple interest. I'll just go back to the PowerPoint. And the next application where we can use recurrence models in this, or linear recurrence models, is in flat rate depreciation. So we'll have a look at that. Now we'll go to 3.1. Notice it's 3.1 because it's a new problem and we don't want the variable values to be muddied. So in flat rate depreciation, rather than an investment that increases, this is the value of an asset that might decrease in value, so it decays in value. So that's the idea of growth with simple interest and decay with something like depreciation. So in flat rate depreciation, it's very much like simple interest in the sense that it's the same amount that the value is changing by each year. It's just that it's going down instead of it going up. And so you'll notice a difference in the formula, or the standard or the general formula, that recurrence relation. It's V of n plus 1 is V of n minus D, but that's really the main difference. You're taking away how much it depreciates by each year, and the amount it depreciates by each year is constant. That is, it's the same amount you take away. Like with simple interest, you have to work out how much that is. So in this case, it's saying it's decreasing by 5%. So we're removing 5% of the value of the original value every year. So the calculation for D says that this asset would lose $600 a year. The recurrence rule specific to this then is V of n plus 1 is just V of n minus 600, where the V naught was 12,000. So we're saying the asset was originally $12,000, say, in value. Okay, there is an associated direct rule which you use for other calculations where you want to know, for how long, when does it get to a particular value, or what is the value after 12 years, things like that. Okay, so the direct rule in our case is V of n is 12,000 minus n times 600. So it's dropping by $600 every year. Again, in the notes page, we've set up a thing for substitution, so you can put in, if you know it's 5 years, then the formula or the direct rule will tell you that V of n, or V of 5, is 12,000 minus 5 lots of 600, and that's $9,000. So after 5 years, that asset is now worth $9,000. As in previous pages, you can get a quick look at the progress over 5 years, and you can also work out how many years it would take for the value of the asset to get to, in that case, $1,000, and it's 18 1/3, it looks like, years. And you probably would say, because it's complete years, you probably should say that it ends 19 years before it gets below $1,000. Okay, so that's a template that can be used to analyse flat rate depreciation. Now, you might also need to do other calculations for particular questions that are slightly different. And for that reason, I've kept in this file a page which is just for calculations. Okay, so I'll just jump back to the PowerPoint and we'll do the final application, which is another style of depreciation which isn't based on a fixed amount of reduction in value each year. It's based on usage. And so things like cars might depreciate by unit cost based on the number of kilometres that it travels, or say a photocopier its value might be based on how many copies it's done. So we'll now jump to the final template. And I think it should say 4.1. Let's keep going. There it is. So looks quite familiar, and a couple of things that are different. So like flat rate depreciation, you'll notice that it's V of n plus 1 is V of n minus D, given in V naught. So depreciation that shares that notation. And now, the thing that's a little bit different about this is that the amount that it depreciates is based on a per use or a per the number of units used. So let's say that the original value is 25,000. So V naught is 25,000. And let's say you know that it gets to 8,000 in value when 80,000 units have been run or been used up. And so the D value, so the way of calculating the D value in this case is to say, well, what's the difference in the value? How much has it dropped in value? So it's dropped from 25 grand to 8 grand. And then you divide it by the number of units, so number of copies or a number of kilometres, and that will give you what's called a per unit cost, or what they just call the unit cost. So it looks like that is dropping by about 21 cents per unit, or per copy, or per kilometre, whatever the story was. Okay, so now you've calculated the D value. It's pretty much as before. The direct rule is V of n equals V of naught minus n times D. And then the direct rule in our particular case is 25,000, the original value, minus the number of units times the sort of 21 cents, if you like, or $0.2125 per unit. So now you can make a calculation such as, if you know the number of units, you can work out what the value should be after that much use of the asset. And then similarly, you can say, okay, well, if the value is 10,000, what does that mean in terms of the amount of usage that particular asset has had? And so similarly, before, you'll notice that there's a solve command for that. You'll also notice that there's no sequence showing you the first few terms. And I guess that's because a single unit of use is not so significant for unit cost depreciation. You're interested in the thousands or hundreds of thousands or millions, depending on the story. And so just showing the first 5 numbers in that sequence is less useful. Okay, so as I said, this particular approach is to help with the common sort of calculations that you do for linear recurrence rules and their use in modelling simple interest calculations and flat rate and unit cost depreciation. Most of the questions seem to be on those sorts of ideas, and so you might find this calculation tool quite handy. The file RFM linear will be available to you some stage after this webinar, and access to a worksheet which has a couple of, well, has a number of practice questions where you may choose to use this file to help you calculate, or you can do it all without it. It's not essential that you use the notes pages, but it's just a useful resource for you. Okay, well, I think that's probably it. So I might just finish up now.